When we study a vector space, we usually analyze operators one at a time, but often we need to simplify an entire system of linear transformations simultaneously. How do we force every operator into a unified geometric alignment? The formal logic for this problem is detailed in sections 6.5 and 6.6 of Hoffman and Kunze's linear algebra. The baseline concept is straightforward. Diagonalizing a single matrix requires us to find a basis of eigenvectors for that specific operator. Diagonalizing multiple matrices together is more restrictive. We must find a single shared basis where every operator in the system becomes diagonal. Our focus is on the exact algebraic conditions that make this shared simplification possible. Finding these shared structures allows us to decompose a vector space into its simplest independent components. This split screen illustrates our two structural goals. On the left is simultaneous triangulation, finding a basis where operators become upper triangular. On the right, simultaneous diagonalization reduces operators to diagonal form, with zeros everywhere else. For either of these to happen, the operators must commute. S times t must equal t times s. Geometrically, whether we apply s then t or t then s, the vector resolves to the same location. Because of this property, an eigenvector of t processed by operator s will result in a vector that is still an eigenvector of t. Commutativity is the algebraic indicator of a shared geometric architecture. It proves the operators respect each other's eigenspaces. This leads to Theorem 8. If a family of operators commutes and each individual operator is diagonalizable, then the entire family can be simultaneously diagonalizable. Let's test this. Here are two diagonalizable matrices, A and B. First, we calculate the product A times B. Then we calculate B times A. The results are identical. AB equals BA. This confirms they commute, sharing a basis of eigenvectors. Using these shared eigenvectors, we can construct a single transformation matrix, P. This matrix simultaneously diagonalizes both A and B. By leveraging the shared geometric structure, we can analyze the behavior of both operators using the same basis. Shifting our focus from the operators to the space they operate on, we can examine how to partition a vector space V. This defines a direct sum, decomposing a space into independent invariant subspaces. The symbol signifies geometric isolation. They only overlap at the zero vector. Consequently, any vector alpha has exactly one representation as a sum of specific component vectors. This uniqueness ensures that mathematical operations performed within one subspace will not affect the data in another. To isolate these components, we use projection operators, denoted as E. Projections follow three rules. First, idempotence. E squared equals E. Applying the projection filters the vector. Applying it again does nothing. Second, orthogonality. EI times EJ equals 0. Mismatched components are zeroed out. Third, completeness. Summing all projection operators reconstructs the identity matrix. Projections are the functional engines of the direct sum. They allow us to calculate and isolate specific pieces of a vector space. We can see this in example 11 from the text. We start with a finite dimensional space V with a standard basis. Each individual basis vector spans its own one-dimensional subspace, showing that V is the direct sum of these independent lines. Example 13 connects this back to operators. A diagonalizable operator T decomposes the space V into its characteristic eigenspaces. This links each algebraic projection to a specific geometric zone. Ultimately, finding a shared basis for commuting matrices and identifying projection operators for a direct sum fulfill the same objective, reducing complexity into independent, analyzable parts. To summarize, first, commuting operators share geometric structure, preserving each other's invariant subspaces. Second, simultaneous diagonalization allows us to analyze families of linear operators using a single shared basis. Third, direct sums partition vector spaces into independent, manageable invariant subspaces. If you found this helpful, like the video and subscribe for more clear explanations from Hoffman and Kunze linear algebra.